Hey everyone, my name's Taylor Sparks. I'm the editor-in-chief at Integrating Materials and Manufacturing Innovation, and I've got a new paper to talk about today. It's FAIRification of legacy devices and measurement applications with single board computers. Now, you might not be familiar with the word single board computers, but they're talking about these things, right? Like that little Arduino device that I built for my dog's fabulous dog collar, or for my kids' Pioneer Derby cart with a little accelerometer. These things are amazing. You can come up with tons of cool applications for them. They come in all sorts of shapes. Some of them have breakout boards. Some of them are independent. Here's one where you can actually, it's meant for being sewed onto clothing for wearable electronics. Like they come in every sort of shape and size, and they're awesome. My own group has been using these for the basis of low-cost self-driving laboratories. Here's our Hello World using basically the light mixer here in the sensor. So they're all over the place. So what are we talking about here in this paper with authors from Bremen, Germany, Riefler, Mädler, and Steinbacher? They're talking about how these same devices, these low-cost devices, can be used to achieve FAIR principles. Now, a reminder, FAIR stands for findable, accessible, interoperable, and reusable. We want the data that we generate as scientists to be useful. We want people to be able to use this data, and they think that these boards, single board computers, could be an opportunity to make that more possible. They point out that many of the instrumentation available in labs is controlled by computers with operating systems that get outdated. I know I've experienced that. We had an old computer that ran one of our laser flash systems that ran on Microsoft XP. Nobody dared touch the thing because that thing's out of date. And once it breaks, no one knows how to make sure it works. Managing versions is a real issue. Some legacy devices, they point out, have no network capability at all, meaning the only way to get the data on and off was with maybe a thumb drive or something like that. Not ideal. Really what we'd like is for all of our devices to be connected so that we could have FAIR data handling. They point out that the aim is to fully comply with good laboratory practice by digitizing the research process in order to make the methods and outcomes of all of this sort of comprehensible. And this is what we were hoping for with electronic lab notebooks, but it's been challenging. They put forward the hypothesis that the boon of open hardware and open software should make it easier than ever to start to fairify or achieve FAIRification is what they're calling it here. And they give you some cool examples. One of the things I like about this paper is, for example, this first figure, they're helping you select the right hardware. Do you actually need a single board computer? Or do you just need like a digital multimeter with a USB interface? And they sort of ask, is the interface needed? Is internet needed? Here's your different options that are available. And then they get a little more detailed. They say, well, what is it that you're actually trying to capture? What's the device or the process characteristics? In other words, the amount and the kind of data. Is it processing? Is it a measuring device? And then you ask, all right, let's pick the right hardware, which is sometimes just the single board computer, but sometimes might be interfaces, right? So that you can pick the right things to get current or voltage in and out. And then finally, what is the writing control program, right? Is it going to be a GUI or is it simply connectivity? And then in the rest of the paper, they've got really cool examples of this put in action. I like this first one. They're talking about the coronavirus epidemic. If you remember those crazy times, we all had these little CO2 monitoring devices in classrooms, right? And they got so popular that they sold out like immediately and it wasn't able to buy them even anymore. But here they give an example of how easy that is to build. All you need is a Raspberry Pi, a general input-output interface shield, they used a Joyet Explorer 700, and then a CO2 sensor. So for minimal cost, you can actually build this thing and you could capture that data. Now, more relevant to material science and manufacturing, how often do you see a sample that gets processed in a furnace? They'll say that it was sintered at 1200 C for 9 hours or something. Well, does anybody actually log that data? Not very often, but you could. In fact, you could track what was being logged, the file name, who was the operator, what time of day. Here's an example that they show. On the left, you have a picture of the furnace control cabinet, and on the right, they've modified it to include a TFT touchpad with a Raspberry Pi screwed onto the back. You can see it in this picture, where it's really small and it's been screwed onto the back, so that as people run their different samples, that information can get logged and captured automatically. You don't have to worry about necessarily pulling it out of a lab notebook. This is able to get fed immediately to an electronic lab notebook. They've got a bunch of other examples. Here's one for monitoring hydrogen gas in a tube furnace where they can actually get real-time data logging. Super valuable stuff if you want to make sure that your experiment is doing what you think it's doing. Talk about this as a gateway for other electronic lab notebooks. I just think this is a really cool paper, and I hope that you'll check it out and learn a little bit more about their attempt to achieve FAIRification of legacy devices using these ever increasingly popular single board computers and other devices.